We can have a tap resistors. These tap resistors are nothing but a wire-wound fixed resistors having one or more additional terminals along its length. See, you can see that this is one terminal, this is second terminal, we will have a third terminal over here. So wire-wound fixed resistors having one or more additional terminals along its length are used to reduce current flow, adjust signal levels, to divide voltages, bias active elements, and terminate transmission lines are the usage of this particular tap resistors. Potentiometer, you have seen, is used in circuits to vary the magnitude of resistance passing through the resistors. Trim resistors or presets, we can say that, is a miniature variable resistor, we can say rheostat, used mainly in place of a fixed resistor, permit convenient adjustment of resistance in a circuit. And LDR. LDRs are nothing but what? LDRs are nothing but light dependent resistors used to detect levels, light levels. For example, in automatic security lights, see, LDR's resistance decreases as the light intensity decreases. In the dark and at low light levels, the resistance of an LDR is high and little current can flow through it. So these are nothing but devices that do not change the resistance as exposed to the external photon sources. You can see this is a metal contact. This is a cadmium sulfide track. Now let's understand the next passive components called as capacitors, because we have given an example of passive as resistors, capacitors, and inductors. So the second is capacitor. Electrical device consists of two plates separated by an insulator called dielectric and has the capability to charge and discharge voltage. How you will define capacitor? An ability to store an electrical energy can be called as a capacitor, isn't it? And the medium between the two plates of the capacitor can be called as a dielectric medium. So a capacitor is a device that stores an electrical charge. A capacitor consists of two conductors separated by an insulator. How the symbol is drawn? This is a two equal parallel lines. Two equal parallel lines are the symbol for capacitor. If they are unparalleled, then that will be a symbol for DC source. Now you have two types of capacitor. One is parallel plate capacitor and the other is called as a cylindrical capacitor. Now you can see that these are the two plates which are parallel and equal in size, and the medium between these two plates define the types of the capacitor. The other is cylindrical cylindrical capacitors. Now you can see here, a cylindrical capacitor is a parallel plate capacitor that has been rolled up with an insulating layer between the plates. So here you can see that this brown sheet, this brown color sheet is nothing but an insulator between the two plates of the capacitor. Now just take here one capacitor. So these are the two plates of the capacitor and we have given an electromotive force of the value of 12 voltage. Then this particular left side plate will be into the positive and this is into the negative charge. So this is a symbol for the capacitance, two equal parallel lines. And this is the voltage, and how we can define the C value. A capacitor in a simple electric circuit. So charge, electrical charge stored in a capacitor can be written as in Q. So this charge is nothing but a charge on the condenser, which is defined as Q is equal to the value of C and the voltage applied. Say this capacitor, we say it is fully charged when the potential difference across these two plates of the condenser is equal to the applied voltage. So if we measure the voltage across these two plates as a 12 voltage, then we can say that this particular condenser is fully charged. And once this particular condenser is fully charged, then it starts blocking the further flow of current through the condenser. And that fully charged value is given as Q is equal to maximum charge value. Q should be equal to C into V. So the stored charge value Q is proportional to the potential difference V between the plates. The capacitance C is the constant of proportionality measured in farads. So the unit for the capacitance are farad, whereas the units for resistance is ohms. Like condenser, like the resistance, we have condensers also of fixed capacitors as well as a variable capacitors. Under the fixed capacitor, if you classify it, they are electrostatic capacitors, mica capacitors, ceramic capacitors, paper capacitors. Whereas under the variable capacitors, you have gang capacitors, trimmers, and paddles. We will see each of the capacitor in the next slides. Let's understand what are fixed capacitors. Capacitors whose capacitance value is fixed. We cannot change the value of condenser, we cannot change the value of capacitor. So those are called as fixed capacitors. Under this, you have electrolytic capacitors. An electrolytic capacitors are a type of capacitors that is polarized. You can see these two wires to the condenser are not of the equal length. It means the small length wire is -1 and the bigger one is called as an anode. This is positive and this is cathode. An electrolytic capacitor are a type of capacitor that is polarized, made up of aluminum plates and oxide as dielectric. They are able to offer high capacitance value, typically above 1 microfarad. And the applications are low frequency applications, power supplies, decoupling, and audio coupling applications, as they have frequency limit if around 100 kilohertz. Mica capacitor. Mica capacitors are not polarized. What is not polarized? A non-polarized capacitor is a type of capacitor that has no implicit polarity. See, you can see these two metal wires are equal length, whereas here you can see these are unequal. Unequal in the sense the shorter length says it is a negative and the bigger length says it is a positive. Whereas in the case of mica capacitor, they are non-polarized. It means both the terminals, both the metal wires are of the equal length. So it can be connected either way in the circuit because they are not polarized. Mica capacitor have the range of 5 to 10,000 picofarad, rated up to 500 volt, and the applications are high frequency applications like resonance circuits and high frequency filters. Ceramic capacitors are also not polarized. In fact, the non-polarized capacitors examples can be ceramic, mica, and some electrolyte capacitors. So this is non-polarized, made up of silver or copper plates, and titanium or barium as a dielectric medium. Ranges from 3 picofarad to 2 microfarad, and high frequency applications. This is how it looks like. So these are all called ceramic capacitors. See, they have the value printed onto the capacitor, like 2, 2, 3, or 500 voltage and all. We will understand how the labeling of the capacitors are done. Next are paper capacitors. It is also not non-polarized. It means either of the way we can connect into the circuit. Made up of aluminum foil separated by strips of paper soaked in dielectric, and that dielectric medium we can take it as in wax or plastic or oil. So here we can say that this is paper soaked in a dielectric, and this white one we can say that this is an aluminum foil. So disadvantages is large in sizes, as you can see here, it is a large in size. Applications are high voltage applications. Now the variable capacitor. Capacitor whose capacitance value can be varied. So if you have an option to change the value of capacitor, then that particular capacitor are called as a variable capacitor. So example for the variable capacitors are gang capacitors. These are rotor stator arrangement with two sets of metal plates. You can see here. Fixed plates stator, movable plates are rotor. Movable plate connected to the shaft of capacitance, and capacitance is varied by rotating the shaft. This is the shaft where which we can rotate it. And applications are tuning of radio receivers. If you see the old type of radio instrument, there for the radio receiver we used to tune it to match the particular bandwidth. So for that we used to use a gang capacitors. These are trimmers. Construction metal plates separated by a dielectric. It can be mica or ceramic. Capacitance variation is done by rotating the screw. So here, this is the circuit of that particular trimmer. So by rotating this particular screw, we can vary the value of capacitance. So this is the plate. This is made up of mica or ceramic. So the two plates are, say this is one plate, okay, and the beneath plate is this one. This is the second plate, because it should be made up of two plates between the medium, intermediate medium, and this intermediate medium we have taken out of mica. So as you rotate clockwise as well as anti-clockwise, you can see that this plate will come in close to this particular medium or away from this medium. It means we are changing the value of capacitance. So this is called trimmer. So capacitance variation is done by rotating the screw, this screw. And the range is in picofarad. Applications are used where tuning is not very frequent. Tuning of broadcast receivers. See, broadcasting, transmitting or receiving, once the signal is tuned, once the resonance occurs, resonance are nothing but when the force vibrations matches the natural vibrations, then the resonance occurs, or we say tuning occurs. So once the tuning is occurred, we don't use again and again to change the value of C. So there in that kind of an applications, the trimmers are used. So used where tuning is not required, not very frequent. So tuning, example are tuning of broadcast receivers. These are called padders. It's a variable capacitors. Again, you can see here. Say this is a plate, this and this complete will give one plate of the condenser, okay? Whereas this will give the another plate of the condenser. And between these two plates, there is a medium. And here you have taken a screw, or this is a nut. So by rotating the screw, we can change the value of a capacitance. This is a screw, we can see here. This is a screw. Then it is constructed through an aluminum plate separated by a dielectric or air. Capacitance variation is done by rotating the screw, which have the ranges of 5 picofarad to 600 picofarad. So these are called as a padder. How the numbering of capacitors are done? So numbers, if it is greater than 1, is called picofarad. Numbers which are less than 1 are called as an microfarad. So it is greater than 1. If I say this is a 10, so this value are in the form of picofarad. If it is less than 1, then that are called as in the value of microfarad. See here 104. It is written just printed as in 104. 104 in the sense 10 and 4 zeros. 1, 2, 3, 4. So 10, like we can say that 100,000 picofarad. So this have the value of 100,000 picofarad. Now you can see that 10 means 10K, 10K means 10K picofarad, like 4K7 means 4.7 kilo picofarad, 2M2 means 2.2 mega picofarad. Similarly, 47M means 47 nanofarad. 47M means 47M megafarad. And if it is 104K means 10% and 104M means 20% tolerance. Here again we have a tolerance of 10% to 20%, depends how it is printed onto that. So if it is written 104K, it is a 10%, and it is written 104M, it is a 20% tolerance. So this is how the numbering of capacitors are done. Now if we summarize the capacitors, 6 type of capacitor. This is a fixed capacitor which is polarized. This is again a polarized capacitor, electrolytic or tantalum. This is how it looks like. This is minus and plus. Non-polarized capacitors are called as an AC capacitor, needed at AC application in series or in parallel with the signal. Or we have a varactor capacitor, or can be called as a capacitor diode, are commonly found in communication equipment where electronic tuning is necessary. They are an important component of radio frequency or RF applications. Trimmers, nothing but a variable, having a variable capacitor using for making fine adjustments. And tuning capacitors, as we studied about the GAN capacitor. In a radio is involved in determining the frequency of an oscillator somewhere in the radio. As the capacitance is varied, the frequency of oscillator changes. Now let's understand the third component called, for the example, for the passive components called as in transformers or inductors. A coil is an inductor used in electronic circuit to introduce inductance. So how you will define an inductor? Inductors are an electrical device formed by insulating wire wound in a coil around a core having the capability to store energy in its electromagnetic field. Inductors are frequently found in tuning and filtering circuits. What are the laws of induction? When an electrical current flows through a coil wire, an electromotive force will be generated in such a way that it opposes the flow of current. So if you understand the Maxwell's relation between electricity and magnetism, like any current carrying conductor will have surrounding to that, there will be a varying magnetic field. These are a symbol for the inductors. That is, this is air core, like nothing between the coil. So this is air core symbol. If you have taken an iron core and winded a copper wire into that, so to draw that, this is a symbol. This is a ferrite core, dotted 2 lines. This is a straight line, and this is a dotted 2 lines. And this is a variable core, or arrow mark. Okay. This is how the current flows. This is a coil wounded. This is how the coil with a number of turns, like we can say that 1, 2, 3, 4, 5, 6, and so. This is the length of the coil, we can say. This is the inner coil. This we can say the cross-sectional area, and this we can count it as a number of turns. So voltage is measured between these 2 points, and current is how it is passing through that. So this is basically a symbol of an inductor. Value specified in Henry. or millihenry or microhenry. So Henry, millihenry is nothing but 10 to the power of -3. Microhenry is nothing but 10 to the power of -6 henries. Inductance is the property of inductors by which it opposes any change in the flow of current. So if you understand the Faraday's law of electromagnetic induction, how the electromagnetic or how we have taken the magnetic flux is directly proportional to I. Phi was proportional to I, or we have studied d phi by dt is proportional to I, and how d phi by dt is equal to L into I, and that L is nothing but inductance measured in Henry. A coil of wire that may be wound on a core of air or other non-magnetic material or on a magnetic core such as an iron, powder or ferrite. Two coils magnetically coupled form a transformer. Now we were talking about a air core or a copper core, or we can take a ferrite and we can have a copper wire winded over into that. But if you have a two coils magnetically coupled and kept beside to each other, then that forms a transformer. These are the types of transformer. As you can see here, these were the symbols: iron core, air core, and ferrite core. Similarly, you can see here, this is a ferrite material and wounded with a copper wire. So this is a ferrite core. There is nothing between this particular winding. This is air core inductor, and we have taken an iron. So this can be called as an iron core inductor. So these are the types of inductors. Now, if you take the two inductors magnetically place one beside the other, then that forms a transformer. And this is a transformer design, we can say that. So there are two coils. This is one coil and this is a secondary coil. So what happening is, this is called as in a primary coil, this is called as in secondary coil. Then this is an iron core, laminated iron core. Then this is number of turns in the primary coil, NP. These are number of turns in the secondary coil, NS. So we are giving an input to this particular transformer as a sinusoidal wave, an AC input. And what happening is, onto the secondary coil, we can see that there is a current across this particular load. So this works with a principle of electromagnetic induction or mutual inductance principle. What is happening is, when an alternating current is passed through this particular coil, surrounding to this particular coil, a varying magnetic field is generated. And within this vicinity of this particular varying magnetic field, if I place one more coil, an induced EMF will be formed into this particular secondary coil. And because of the induced EMF in the secondary coil, there will be a current flowing in the secondary coil. And if I place a bulb or any load, we can see that the bulb is glowing in the secondary coil. Understood? So it is a principle of electromagnetic induction. We cannot say here there is no voltage into the secondary coil, but still the current is flowing in the secondary. So that is because of the mutual induction principle. How you define the transformer? It is a static piece of apparatus by means of which an electrical power is transferred from one alternating current circuit to another electrical circuit. See, transformer will not change the nature of the current. This is an input given as an AC. The output is again into the form of same nature, in the form of AC only. So always remember, transformer will not change or convert the nature of the current in the output. Current or voltage. There is no electrical contact between them. The desired change in voltage or current without any change in frequency. It means if you have an input AC with a frequency of 50 Hz, the output will have the same frequency value of 50 Hz AC. It works on the principle of mutual induction. This was the first transformer made at Germany, Budapest, in the year 1885, and it is still placed in the one of the Josh Museum, Germany. So you can see the two coils. One is primary and the secondary coil. Now, two types of transformer we have: step down as well as step up transformer. So you can see the symbol of the transformer in this manner. This is a primary winding and this is the secondary winding with the two equal parallel lines. A step down transformer is one whose secondary windings are less than the primary windings. In other words, the transformer secondary voltage is less than the primary voltage. So the transformer is designed to convert high voltage, low current power into low voltage, high current power, and it is mainly used in domestic applications. If you can see onto the circuit diagram, the number of windings in the secondary coil is much lesser than the primary coil. So what will happen, as we said, that when an alternating current is passing through this particular coil, surrounding to this particular coil, there will be a varying magnetic field. And in the particular area of that particular varying magnetic field, we have placed one more coil. This is nothing but called as a secondary coil. And there will be an induced EMF in this particular secondary coil, and the current can be seen in the secondary coil. So if you have a less number of turns on the secondary coil, less induced EMF can be seen in the secondary coil. So the transformer is designed in such a manner which converts high voltage which have a low current power into a low voltage which will be having high current power. So this is called step down transformer, basically used for any domestic appliances, especially mobile charger. If you take a mobile charger, we use a transformer because it have to step down from 220 voltage input here to a 5 voltage output, and that 5 voltage output AC should be again converted to a DC form. That DC pure form is used for a mobile charger. So basically a charger will have a transformer, that too a transformer which is a step down transformer which will convert a 220 voltage to a 5 voltage AC, and that 5 voltage AC should be converted to a 5 voltage DC. It means a rectification is happening over there, and that DC pure voltage output is given as an input to the mobile to make our mobile charger every day. Here is step up transformer. So what is step up transformer? If you can see that this is a low voltage converted to a high voltage. So number of turns on the primary coil is less compared to the secondary coil. So we can say that the induced EMF will be in a multiple times of the primary coil because the number of turns in the secondary coils is more. So it is made in such a manner where the low voltage high power current is converted to high voltage low power current. So this is called as a step up transformer. Basically we used for the apartments, because for a single house we can adjust with a 220 voltage to run our all home appliances, but the same 220 voltage cannot be sufficient for 10 families which are staying in an apartment. So we use a transformer which is called as a step up transformer. For an example, the same 220 voltage can be multiplied into 10 times using a high number of turns onto the secondary coil. So here we say that the 220 voltage is input, whereas the output is 2200 voltage, because we have multiplied the input voltage into 10 times, and that particular 220 voltage will be sufficient for a 10 families who are residing into a apartment. So that the basic application of step up transformer. One more type, it is called as an intermediate frequency transformer, which works at a frequency of 455 kilohertz and cased with aluminum can. You can see this. Tuning is achieved by using parallel capacitors across primary and secondary windings. And applications are basically radio receivers. So these are called as an IF transformers, intermediate frequency transformers. The next is audio frequency transformers. Basically, we use this into many of the applications. Audio frequency transformers works at a frequency between 20 hertz to 20 kilohertz, which is an audible range, and are used in audio amplifier circuits. They were essentially involved for matching the high impedance outputs of these amplifiers to low impedance loudspeakers, but transistor amplifiers have much less need for output transformers. So this is called an AF transformers, audio frequency transformers, with a range of having a frequency range between 20 hertz to 20 kilohertz. You can see that this is a pressed steel cam. This is just an upper lid, and this is the shell type solid or powdered iron core. You can see this grayish color. Okay, and this is a primary and secondary windings underneath of this. This is a PCB mounting tacks. So for the printed circuit boards, we normally use this particular transformer, which is called an audio frequency transformer, which will have a frequency range between 20 hertz to 20 kilohertz of frequency values. These are the symbols we can see here. How the symbols for different type of inductors are made: fixed air core inductors or fixed ferrite cores, tap air, variable air core, variable ferrite. Here you can see the fixed iron dust core inductors with the dotted two plates, two lines. Fixed iron core inductors. This is a roller coaster variable inductors. So these are all the symbols for different type of inductors for our electronic applications. The next are relays or contactors. So relays, this is the beautifully shown a diagram. High power source, this is a low power source, and here the low power source is winded. Here we have used an inductor, and it's kind of a low power source according to this particular electromagnetic induction. This will work. So this work as a switch. So this mechanism is called as a relay, and here we can see the output. Contactors, when a relay is used to switch a large amount of electrical power through its contacts, it is designated by a special name called as in contactors. You can see this is a relays. Okay, this is in three-phase AC power, and this is the load we have used over here as a motor. Now the few examples are semiconductor families. The first we can see it is in a diode. It is nothing but an electronic device that permits current to pass or to flow in only one direction. So diodes are nothing but it is made up of two materials, P and N. When a P-type material and N-type material are added in the process of crystallization, a new device is formed, and that device is called as a diode. A transistor, if we take up two PN diodes and suitably added, then a transistor is formed, which is nothing but a semiconductor device used for amplification and switching application in an electronic circuit. Basically, a transistor's main applications are amplifiers, or it can be used as in switch circuits. Because transistor characteristics, if you study, it can be used at saturation region or cutoff region. So fully off or fully on. It means switch, or transistor can be used as an amplifier